Okay, so we're going to start a brand new chapter today on function operations. There's going to be a lot of graph drawing that goes on today, so I'm not going to waste your time rambling on here. We're just going to get going. So our new chapter covers function operations. This is just basically where you add, subtract, multiply, and divide separate functions. In terms of an algebraic approach, this is going to look really simple, but in terms of analyzing things, don't get too overconfident here because things can get pretty tricky pretty quick. Anyway, today we're only going to focus on sum and differences of functions. We're also going to look at how this impacts the domain and range, along with what it looks like graphically. Here we go. All right, so sum of functions. A sum of functions is exactly what it sounds like. It's where you add two functions together. So if we had these two functions, f of x and g of x, and we're looking for where h of x is f of x plus g of x, we can literally just say, hold on here, we literally just say h of x is f of x, which is x plus 1, plus g of x, which is 2x minus 5. And then, of course, simplify it up. So h of x equals 3x, and then 1 plus negative 5 is, of course, minus 4. So h of x is 3x minus 4. That's it. That's all there is to it. So an algebraic approach to this, pretty cut and dry, not a big deal. One thing we got to say, though, before we move on, is h of x equals f of x plus g of x. That's probably the easiest way of writing this, but there's some other notations that can come up. There's this one that says h of x equals f plus g. I don't like that one, but it happens every now and then, so just keep an eye out for it. And another one says h of x equals f plus g in brackets of x. So it's like the combination of these of x. I kind of like this one. This one's more common. Just understand, though, that all three of these, so this one where it's f plus g, and this one that I started with, they all mean the exact same thing. So just keep your eye out for that one. All right, next up, sketch the graph of these and then sketch the graph of h of x. Okay, so same question from before. I'm going to try to do this as quick as possible, but you guys know me exactly how amazing I am at drawing a graph here. This is just a linear equation, so start with your y-intercept. Your y-intercept is 1, and your slope is also 1 because it's 1x. So we're going to go up 1 over 1, and so on. So it looks something along the lines of that. Just get all the dots in here. Believe me, the dots are going to be important in just a second here, because I can tell you right now my graph's going to look like garbage here. Oh my goodness, like right at the word go. Here we go. Okay, tracing it. Here we go. I'm going to stop, take a breather. All right, 1, 2. Oh no, goofed up. Here we go. Yeah, all right, stop. Keep going. There we go. Awesome. All right. So that's f of x. I'm going to change pen color now just so the next one sticks out a little bit more. G of x I'll do in blue. 2x minus 5. So our y-intercept is negative 5. And our slope is 2. So we go up 2 over 1, up 2 over 1, up 2 over 1, and so on. Remember, the dots are going to be really important here. So I'm going to make sure I put them all in accurately. I'll save them for a thing we'll do in just a minute here. Throw in the line just so we can say we've done it. Their meeting right there, that's kind of interesting. Good, awesome. All right, next one we're going to draw is h of x. And of course, since we have the function for h of x, it'd probably be easier to do that, at least for now. Remember, it was 3x minus 3, or 3x minus 4, rather. So our y-intercept is negative 4, so I'll start there. And our slope is 3, so we're going to go up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1, and then I'll go down 3 over 1, down 3 over 1. Awesome. All right, and then the line. Oh, there we go. I'm sure this is absolutely thrilling for you guys to watch this right now. Yeah, all right, whatever, got it done. It's not perfect, but you get the idea. All right, so those are the graphs of all three of those. What I want to get at, though, is how could you have used the graphs of f of x and g of x to make h of x? Well, let's just take a quick look at this. I want you to actually analyze this. Look at the red one and look at the blue one, and see what the relationship would be between the red line and the blue line to make the green line. And again, a little hint I gave you earlier about the points being important. Yeah, look at the individual points. See if you can figure this out. If you have to pause the video, go for it, but I'm going to go over it now anyway, just so we don't waste any more time. Hopefully you're able to put together that h of x is the addition of the y values, right? So if you just like pick a given x value, like let's say we start with x is equal to 0, okay? So at x is equal to 0, notice y is 1 and y is negative 5. 1 plus negative 5 is negative 4. So that worked. Then if we look at it where x is 1, we have y is 2, y is -3, and then 2 plus -3 is -1. And if we look at the next one, when x is 2, we have 3 and -1. That adds to 2. Do one more here. When x is 3, we have 5 plus 1, which is 6. Oh, no, sorry, 4 plus 1. See, I was messing things up already. 4 plus 1, that equals 5, right? And so on and so forth, right? You can see the pattern. So basically, when you add two functions together, really all you're doing is you're adding their y values for a specific x. And that can be really useful because sometimes if you know the graph of one function and you know the graph of another function, but knowing the graph of the other function, like the third one, where it's the addition of the two, that can be a little bit weird, okay? So just keep your eyes peeled on that. We're gonna do another example here. This one's gonna be a little more challenging. F of x is x squared. That part isn't too bad. It's just an x squared graph. In case you've forgotten, remember just a normal x squared has a vertex right at 0, 0. A vertex, by the way, on a quadratic is -b over 2a, but since b is 0 here, like the plus bx isn't there, so b is 0, then our vertex is at 0, and then you just plug in the x value of that to find your y, right? Anyway, so x squared is going to start at 0. Then you can use the 149 rule. The 149 rule says when you're dealing with a quadratic, something with a squared in it, you start at your vertex and go over 1 and then up 1 times a. Well, a is just 1 here. It's just 1x squared. So we go over 1 and up 1. And then you go over 2 and then up 4 times a. And then you go over 3 and then up 9 times a. So that's going to make a symmetrical graph like so. And then I'll do my best with this. Again, the points are more important, as you saw on that last question. That's all right. Doing an okay job. All right, there we go. All right, next up, we'll do g of x. G of x is going to be a lot simpler. It's just a linear equation. -4 is where we're starting, and then our slope is 4, so go up 4 over 1, up 4 over 1, up 4 over 1, and then we can reverse the process. That'll be good enough. All right, here we go. Again, those dots are the most important part here, but if you can, at very least, try to draw the line. Awesome. All right, now h of x, we haven't even made a function for that one yet, so we'll start by doing that first. H of x is just f plus g, so it's going to be x squared plus g of x, so plus 4x minus 4. And usually you put brackets around there, but because the plus does nothing on that, we just leave it like so. Now you have some options here. You can draw this like how I introduced last slide, where you just look at the y coordinates, so the dots, and you just add them together. And there's nothing wrong with that. But the only thing that's going to cause you some trouble is pretty much this entire left side of the graph isn't going to get drawn with just the points that we have on here. So you'd have to start playing around by plugging in x values, like x is -5, for instance, into these, and then adding those values together, because that'll give you a y value for each of them. Add those y values together, and that'll give you your h of x. If that seems too much, I understand. I'm personally going to do this the old-fashioned way. I'm going to find the vertex of this. The vertex is going to be -b over 2a, so -4 over 2 times a, so 2 times 1 is 2. That gives me -4 divided by 2, which is -2. And remember, that's the x coordinate of our vertex, so we know our vertex is going to be at -2 somewhere. We just have to find the y value of it. To find the y value of that, you just take -2 and you plug it in here. So -2 squared is 4. 4 plus 4 times -2 is -8, so 4 plus -8 is -4. -4 minus 4 is -8, so y is -8. So -2, -8, that is going to be our vertex right down there. And then I can do the 149 rule on this as well, because again, this is a quadratic. The 149 rule says start at your vertex, go over 1, and then up 1 times a. Well, a is 1 on this case, so go over 1, up 1. Then go over 2, and then up 4 times a, so we're going to go up 4 in this case. And then you go over 3 and up 9 times a. That'll bring us up to +1. And I think on this question, we can actually even do the very rare 149-16 rule, because 16 is the next one in that pattern. So we can go over 4, 1, 2, 3, 4. And then up 16, which is actually going to take us from -8 to +8. And then just make it symmetrical on both sides. And notice how this rule actually really helped us in this question, because this whole left side would be hard to do because none of these y values are even visible on the graph we have. Anyway, I'll do what I can to connect the dots here now. That's about as good as I'm going to make it. There we go. And then holy smokes, this is not a good one. There we go. Awesome. All right, it's good enough. We get the idea. Yeah, and I'll just leave it at that. So again, you could have just added the y values together, but this whole left side of this green graph here would have been tough. You would have had to extrapolate other information from it. So again, there's more than one way of doing this. That's what I kind of want to get at here. Now it says list the domain and range of each of the three functions. Notice any relation. How about we just make a little chart? Domain, range, and then we'll start with f of x. F of x is the red one there. Look at the domain. The domain's your possible x values. I see nothing that could be restricted, so I'll just say x is an element of the real numbers. As for your range, there is a bit of a restriction. Y has to be greater than or equal to 0. All right? Now, what I want you to notice as we go through these, I want to see if you can determine if there's any relationship between the domain of f of x and g of x and the domain and range of h of x. All right? So we'll move on to g of x next. G of x is really nice. It's a linear equation. Linear equations have an unlimited domain. There you go, unlimited domain, as well as an unlimited range. So we're good there. Now, h of x, on the other hand, let's just inspect the graph we drew. Is there any issue with our domain? Certainly doesn't look like it. So I'll say x is an element of the real numbers for our domain. But what about our range? What would be the range of h of x? Well, it looks like our range is going to be y has to be greater than or equal to the lowest point on it, which is -8. Now, I want you to think, is there any relationship between the domain of f of x and g of x and the domain of h of x? Well, there kind of is, and it might not be super obvious on this one, but how this works is your domains are going to overlap. So it's the overlap, not the overlap, the overlap of the original two domains is going to produce the domain of h of x. But since both of these had a full-blown domain, the overlap of those is still a full-blown domain, so we're fine. As for our range, they're actually, as far as I've been able to determine, there is not a relationship. I just call it a wild card. Unfortunately, your range is going to be super unpredictable. In order to determine the range of your new produced function by adding your functions together, you just have to graph it. Like there is no way around it. You have to graph it, and you have to inspect what your graph looks like. So in other words, just graph. Okay, that's about as good as we get. And I know that's not a satisfying answer, but that is how it goes. Now, just to illustrate the domain point, because I don't remember if I have a question in here later on, let's suppose we also had another function on here that was like a limited domain, so like a square root function. So maybe it looks something like this. Like the square root graph would look something along the lines of this. Remember, it's like an arch. We'll call this I of x, just because we've used the other letters here. And we'll say I of x is the square root of x. Okay, I didn't draw it perfectly, but you get the idea. Now, with this kind of a square root graph, you can't have an x that's less than 0. So let's suppose we wanted to find j of x, which is f plus I. Okay, so it's your f of x graph, the red one here, plus this purple one right here. Now, for all these points right of our y-axis, you'd have no issue. You just add your y values together and you'd be good to go, right? But these values left of the y-axis do actually pose a problem. Now, some people often get confused with this. They say, okay, let's start at like x is -2. Well, then it's going to be 4 plus nothing on the purple one. Oh, so it must be 4. No, that's not how it works, right? So what you have to do is you have to recognize that since this I of x had a limited domain, that limited domain is still going to be the limited domain of your produced function j of x. So j of x would have the exact same domain as I of x, because I of x is just one overlap within those two different domains. Hopefully that makes some sense. Basically, the idea is if you have values at a certain x on this graph, but no values at that x on the other graph, you can't literally just do 4 plus nothing. Nothing is not the same thing as 0 in math. I know that might be a surprise, but nothing literally just means it doesn't exist within the bounds of that function. And I guess another way of seeing that is j of x would be x squared plus the square root of x. From this, if you were to plug in an x that's less than 0, you'd be square rooting a negative number, and that's not possible. So from this, maybe that makes more sense for some of us. Anyway, I'm going to move on. We're going to look at difference of functions this time around, just because for the sake of time, because we've already used a lot of time here. I'm just going to keep my pen. Yeah, and unfortunately, we're only about halfway through, so it will probably be a longer lesson today. So we're going to consider these functions. We've got an absolute value graph. We haven't done that in a while. Absolute value just turns anything that's negative into a positive. So the absolute value of x, in case you've forgotten, is just a very sharp V point. I'm going to do the positive end first. Oops, I guess I'll clear that. There you go. Do the positive end first, and then I'll also do the negative end over here, because when x is -1, the absolute value of -1 is +1. Same with when it's -2, it would be +2, +3, +4, and so on. And again, these points are super important, so I'm going to make sure I get them placed, and then I'll draw my line. least as best as I can. That wasn't too bad. This negative side I'll probably butcher. It's not horrible so far. Do it in little pieces. It makes it a little easier for me. There we go. All right, now g of x. Let's see, what's another color we could use? I'll use green for g of x. Whatever, got like Joker colors going on here. -2 is where we're starting, and then we have a slope of 1. It's going to look like this. That's actually kind of interesting. It's like just running parallel to the other one, which I suppose makes perfect sense because I think you would have learned, I think it was Math 10C, you would have learned if they have the same slope, they're going to be parallel to each other. And that's also actually perpendicular to this other line because there's a 90-degree angle. So whatever, we don't need to talk about that. I'll just get this drawn. Here we go. And we're good to go. Okay, so I'll switch colors now. Let's do, we'll do blue for h of x. Notice h of x is f minus g of x. So we're actually subtracting this time around, okay? So what we'll say is h of x is f of x, so absolute value of x, minus g of x. Now this is where you're gonna be careful. When you subtract, of course, subtraction can cause some changes here. So I'm gonna be very safe and I'm gonna go minus x minus 2. And then, of course, we can rearrange this now to say h of x equals the absolute value of x minus x, and then minus 2 is plus 2. Okay. Now, if you were to ask me right now, how can we just draw this? Like, remember on the last one, I said, oh, just find your vertex because it was a quadratic and then do your 149 rule. Well, this is like a weird composed function of like an absolute value and then like a linear equation as well, subtracted into it. So it's really, really quite bizarre. For something like this, this is what's illustrating why we're learning this in the first place. This kind of function would be pretty tough to do without just like literally just plotting at one point at a time. But since we have the other graphs that it's composed from, we can actually graph it just by analyzing those other graphs. So just like when we were adding functions together, this is going to work the same way. We can just subtract the y values to find this. And remember though, since it's f of x minus g of x, we have to take the f of x numbers and then subtract the g of x numbers. So let's start with 0, just because I think that's a good starting point. 0 minus -2. Well, 0 minus -2 is actually going to give us positive 2. And then we have, at x is 1, we have 1 minus -1. Well, 1 minus -1 is actually also, curiously enough, positive 2. What about this one? 2 minus 0 is also 2. This is really weird. 3 minus 1 is 2. What the heck? 4 minus 2 is 2. 5 minus 3 is 2, and I think you're seeing the relationship there. It's just going to be 2 all the way across. Okay, that's really weird. Now let's look at this portion of this, see if it's any different, because I don't want us to draw a horizontal line right now. Let's look at x is -1. We got 1 minus -3. 1 minus -3, I guess, would be 4. And then we look at -2. We got 2 minus -4. That would be 6. And then we got at -3, we got 3 minus -5, that would be 8. I think I'm seeing a pattern now. And then we'll look at -4, we got 4 minus -6, well, that'll be 10. And I think that's as far as we can go. Connect our dots here. This is going to be really bizarre. There we go. That's actually going to be our graph. Looks like it's like a clock or something like that. It looks like it's like 5 to 3 or something. Anyway, that right there would be our graph for that one, and I would never have predicted that just by judging by this equation right here. But that's why these adding and subtracting functions can be actually quite useful. You can just add or subtract your y values together and find what you're looking for. Kind of cool. All right, so from the previous example, state the domain and range of all 3 functions. So kind of like before, we'll do it like this, where we have domain and range. And then I'll start with f of x. Don't mind me, I'm just going to pop back. Let's look at domain of f of x. F of x is the purple one. Our domain, I think, would be all real numbers. There's nothing wrong with that. So x is an element of the real numbers. And our range on this one is going to be y must be greater than or equal to 0. Oops. Y must be greater than or equal to 0. G of x, on the other hand, that's going to be our green one, I think it was. Yeah. G of x is going to have an unrestricted domain and range. So we can just say our domain is x is an element of the real numbers. And y is an element of the real numbers. And then now for the fun part, h of x. That was the one we did in blue. It looks like our domain is actually unrestricted as well. Like we could go on to negative infinity, no problem over there. But our range is y must be greater than or equal to 2, right? From here onwards, we are never going to drop below 2. It's just going to stay steady at 2 from there on. So we'll say again, x is an element of the real numbers, and y is greater than or equal to 2. Just like the one we looked at before, your domain is certainly an overlap of these two. They have an unlimited domain, so there was no issue there. But your range is a total wild card. Looking at these ranges, you would never have predicted this. So that's why it's so important to graph it, just to find that range. So is h of x equals f minus g of x? Is that the same as h of x is g minus f of x? What are the similarities and differences? Well, the answer here is a resounding no. They are not the same. Because again, with subtraction, order matters. I guess the similarities, that's a bit of a tough one. Similarities should be the domain remains the same. So a similarity is domain is the same. There might be some other similarities. I'm just going to run through this. A difference, however, what's kind of interesting is when you subtract things in a different order, really that's like taking this one, so f minus g of x, and it's like timesing it by -1. So we could say it's like -1 times g minus f of x. And as we know from before, multiplying something by -1 is just a vertical reflection. So really a difference is that they're a vertical reflection of one another. That's a little bit more advanced, so I don't think you really need to know that, but it's just kind of an FYI. Anyway, let's move on. Now, why do we care? Well, yeah, that's a real big question, isn't it? So there are many applications for sum and differences of functions. Recall from the exponential functions chapter, that was one we just did a couple weeks ago, that you can model population growth and decay with the function y equals a times b to the power of t over p. Now, I want you to suppose every municipality in Alberta, so every city and town and village, etc., in Alberta modeled their population with this style of an equation. So every single city, we got Lethbridge, we got Calgary, we got Brooks, we got Edmonton, we got all these different places that are going to model their population using this function. What would be the purpose of the sum of all these functions? Right? So in other words, the population growth model for Lethbridge plus the population growth model for Calgary plus blah, 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 right? What would be the purpose of that? Well, I think it's actually quite clear. It would give you a population growth model for literally all of Alberta. Now, I'm sure you could make one for Alberta in this form on its own, but you could also say that Alberta is the sum of a bunch of different cities' growth population models, right? Now, graphically, again, like let's say like Lethbridge had one that maybe looks like this, and then maybe like we got like Calgary, which is like, this is not really going to be drawn to scale. Maybe it looks more like this. Maybe they're not growing quite as fast. Then you got somewhere like Fort McMurray was like this, like a huge growth rate. Oops. And then maybe you got some towns that are actually like doing like a this, where they're going down. If you were to add all those together, remember it's just pick a point. So let's say this point's representing the year 2030, and you can just like add all of those together at that point to get a model for what Alberta's population would be at that year, right? So kind of cool. There's many other different applications of this. This is just the first one that came to my mind, and I'm pretty sure your textbook's got a bunch of applications of this. But yeah, it is pretty useful every now and then. All right, now graphical approach. Just to finish this off one last time, the last few questions here are already graphed for us, thank goodness. Sketch the graph of h of x equals f of x plus g of x. What are the equations for f of x and g of x? Therefore, what's the equation for h of x? Okay, we'll worry about that in a second. Let's worry about graphing this first. So I'll graph this. Since it's an addition, we just add our y values together. So just find some y values that are clear. I don't like when x is -5. This isn't super clear here. I think it probably is +8, but I'm not gonna count on it. So what I'll do is I'll start at -4. So that'll be 7 plus 1. So there we go. We got a point right there. Good. And then we got another one would be right here. We know this y value at -1, so it'd be 2 plus 4. Well, that'd be 6. And then we also have, let's see. We got this one's not super great. I guess what we could do is notice at this point right here we have 0. So we can say that it's going to just be the same as it was right there. We could maybe kind of like Mickey Mouse this one because we know this graph, like f of x graph, is 2. So we could just add 2 to this one. So we go 1, 2. There we go. That looks like it might actually be a pretty straight line right there. And then after that, we could start adding these together as well. So 1 plus 3, that give us 4 right there. And then I guess another one, we could just kind of Mickey Mouse this one too. See at this curve point right here, we have a 3 on the straight line. So we just add 3 to this one. 1. That is 3, right? Yeah, that is 3. Okay, so just 1, 2, 3, and there we go. It's hard to determine for sure whether the relation is going to be perfect, but it's looking like a pretty pointed line. So it'll look something along the lines of this. Okay, so it'll be something like that. That's a good approximation. Now, the next thing this was asking us is, what are the equations for f of x and g of x? I put this in on purpose because I want us to start thinking about what the shapes of graphs are actually representing. F of x is just another one of those absolute value graphs. But remember, f of x being an absolute value graph, usually it's supposed to start at 0, 0. But it's been moved over a few points. Well, how do we move something horizontally 3 points to the right? Hopefully you remember, we can say f of x is an absolute value function, but we're doing a horizontal translation. And remember, horizontal translations happen to replace our x. Okay, so instead of just saying absolute value of x and being done with it, we're going to say the absolute value of x minus 3, because minus 3 on the inside there is going to move it over to the right by 3. Then we have g of x. G of x is like this curved thing going on here. G of x is just going to be an example of a square root graph, and I'm just checking on this one. Square root graphs, if you go over 1 and up 1, yeah, that's a normal square root. If you go over 4, like as if that was x is 4, it should be a square root of 2. Yeah, we went up by 2, so we're good. So in other words, there was no vertical or horizontal stretch on that one, but there is a horizontal translation. Notice it's been moved 5 points to the left. So we can say g of x is actually the square root of x plus 5, because an adding inside of a function moves things to the left. So therefore, since we have all this, what's an equation for h of x? Well, h of x is therefore equal to f of x, so absolute value of x minus 3, plus the square root of x plus 5. Okay? If you want to throw this in your graphing calculator, you're more than welcome to do so. Hopefully it'll look something like what we've kind of put together right here, just less curvy bends in the line. I'm pretty sure those are supposed to be straight, but whatever, you get the idea. Now the last thing here is, what are the domain and range of each function? Let's do our little table as we always have. Domain, range, good. Start with f of x. F of x has an unlimited domain. We're good to go there. F of x's range is y must be greater than or equal to 0. G of x, on the other hand, g of x does not have a total perfect domain. G of x's domain is actually x must be greater than or equal to -5, but the range is y is greater than or equal to 0. Now, next up, we have h of x. This is going to be a domain of also the overlap between these two, and this is what's not super clear about the graph that we were given. The overlap between these two is actually just this guy right here. So the domain of h of x, and maybe you can determine it by looking at this right here, is x still must be greater than or equal to -5. It does not have an unlimited domain, so this does not go on forever. As for our range, good luck determining that. I guess really what I could have done is I could have, yeah, I guess, like, well, we know it's going to be at x3. We could plug 3 into here and do that. Well, I guess we can do that. Y is going to be greater than or equal to whatever on earth this point is here. If you plugged in x is 3 into here, you'll find that this piece is 0, so this piece is gone. So really, we're just doing the square root of 3 plus 5. So I'll just say, just to make our lives easier, y is greater than or equal to the square root of 8, because that'd be 3 plus 5. That's about all there is to it. And that's kind of impressive. We were even able to figure that one out in the first place. All right, I think I have one more question here. Yeah, and this one's just a sketch question, so no more messing around with domain range. Sketch the graph of h of x equals f minus g. Remember, when you're subtracting, it's really, really important that you know which one is which. F of x is this one. It's kind of our absolute value looking one, and then g of x is this straight line. So we just have to take our y values of f of x and minus the y value of g of x from them. You can start wherever you want. I just feel comfortable starting here for some reason. So f of x is 0 minus 2, so we got -2 there. And then we got, no, not that one, we got to be careful, 1 minus 4. 1 minus 4 is -3. And then right here we've got 2 minus 6 is -8. That's going to be, wait, is it? No, not -8. Sorry, what on earth am I doing? 2 minus 6 is -4. My mistake. I don't know what on earth I was talking about there. And then right here we've got 3 minus, oh, it's off the charts. We're not going to worry about that anymore. All right, now we're going to move over to these ones. We got 1 minus 0. Well, 1 minus 0 should be just 1. So we're there. That's kind of interesting how it like really curved all of a sudden. Because yeah, that doesn't look like it's aligned with the other ones. Interesting though. We did that right, didn't we? Yep, 1 minus 0. Yeah, we're good. And then same with over here. We've got 2 minus 2, or minus negative 2. 2 minus negative 2 is 4. And then we got this one here. We got 3 minus negative 4 is 7. That's just going to be right off the chart here, and that's where I'm going to stop on that one. Now, in the in-between here, that's where the real question is. Notice right where these two lines connect, the y value would be the same. So I'm actually going to put like a new auxiliary point here. I'm going to say it's going to be 0 right there. And I know that's kind of unusual, but that helps confirm my suspicion that between these 2 points, it's actually going to be a straight line that connects them. So again, we kind of got like a clock looking thing going on here. It's going to be a straight line up until this point. And after this point, right where we had our little bend here, that's where we're going to have a slight bend in that as well. Okay, so that's going to be our graph. We just sketched that. Again, make sure you subtract them correctly. Don't subtract in the wrong order, because otherwise you're going to get like a vertical reflection of what you actually wanted. And if you want to try that, go for it. But I've already used up way more of your time than I was hoping to. So for practice, here's your practice questions for today. Page 483, questions 1 to 8, 12 to 14. Pick through them, try a few of them, make sure you understand how to do this. Sorry for such a long lesson today. I didn't mean to do that, but of course, when you're graphing, it takes longer than you'd expect. Anyway, best of luck, guys. Reach out to me if you have any questions.